Hello. Hello, everyone, and thank you for attending today's webinar. We're going to be discussing some great topics today. We've got tankless water heaters, we've got stratified tank modeling, we've got experimental evaluation of energy factors. My name is Kyle Glusenkamp. I'm from Oak Ridge National Laboratory, and I'll be your moderator today. Before we begin, just a few housekeeping announcements. First of all, your screen is customizable. Feel free to make the various windows as large or small as you like. You can even minimize them to drop to the menu at the bottom of your screen. And you can click through the widgets at the bottom to be sure you're not missing any of the available options. Presentations can be downloaded as PDFs from the resource list on the menu. A reminder that all of you attendees are in listen-only mode. So you won't be able to orally interact during the session, but please do submit your questions through the Q&A box at any time during the webcast. I'll be monitoring those, and I will present the questions to each speaker after their session. All the presentations will be available for on-demand viewing within a few days on the Engagement Hub. And at the end of the session, we'll be having a chat room on the Zoom platform for anyone who wishes to continue the conversation. And you will be able to interact verbally there. I think there's going to be a link on your screen to the chat room. And let me know if you have any questions. You can submit questions to me through the team chat during the sessions. So on behalf of ACEEE, we wish to first recognize and thank our sponsors for this event. And let me get that slide up here. So we have Rheem and A.O. Smith as our platinum sponsors. Silver sponsors are Bradford White, Green Power EMC, Jackson EMC, NIA, and SoCalGas. And now I would like to introduce our distinguished panel of speakers. They are Alex Friedland from Gas Technology Institute, Noel Merkett from National Renewable Energy Laboratory, and Kashif Nawaz from Oak Ridge National Laboratory. We'll start with our first speaker, who is Alex Friedland. And Alex is a senior engineer with the Building Energy Efficiency Group at GTI. He's an expert in combustion system design for heat pumps and water heaters, whole building energy modeling, and liquid desiccant dehumidification. He has over 10 years of experience in applied and theoretical research in combustion, heat transfer, and thermodynamics. And Dr. Friedland received a BS from the University of Illinois at Urbana-Champaign and a PhD from University of Illinois at Chicago, both in mechanical engineering. So just a quick reminder, the audience is in listen-only mode. Please submit your questions to me through the Q&A, and we'll have a few minutes to ask those to Alex when he completes his presentation. So please take it away, Alex.
Great, thanks, Kyle. Again, yes, my name is Alex Friedland. I'm from GTI. I'll be talking about reduced order modeling of tankless water heaters and combis. This was originally supposed to be 2 talks at the March meeting. That didn't happen. So I'm hoping that this doesn't feel too compressed or rushed. I'm just going to focus on the highlights, but more than happy to answer questions and follow up after the presentation as well. So with regards to the scope of the presentation, I'll just give a little bit of context and motivation for the work that we're doing and why we need the sort of reduced order modeling. Talk about a little bit about the mathematical approach we've taken with tankless water heater modeling, and then how we've been trying to extend that to tankless combi-based systems as well. And then again, just highlight some experimental results or some example simulation results, capabilities, and then talk about a little bit limitations as well. And again, hopefully have enough time for questions. So, this work is essentially, like a multi-year effort at this point for us at GTI to develop tools for modeling advanced gas residential heating systems. And specifically, we've been focusing on so far is, modulating condensing furnaces, gas heat pumps, and combined space and water heating systems. These are either underused or emerging products that, if you want to sort of consider them in your building energy modeling efforts, you'll probably have a hard time finding modules or performance curves that can accurately represent their performance. And so we've been trying to address that. And then we've spoken about this at a few conferences, and there's some publications that are coming out, that have been coming out and will be coming out again in the future. For this talk, I'm just be focusing on our efforts regarding combined space and water heating systems. And really the goal there is to come up with tools that can give you an accurate energy consumption prediction, but do something in a very simple format that can either be used with tools like Energy Plus, or hopefully even derive something even simpler that I'll touch on as well for those maybe not familiar with building energy modeling or are not well versed in those tools. So, for the most part, we work with Energy Plus. There's a number of reasons for that. It's open source, actively developed, widely accepted, and so it's a kind of a good focus for kind of what are the current capabilities for modeling tankless water heaters and combis right now. So if you think about just combis in general, and you look at what capabilities exist within Energy Plus right now, all of the elements for traditional combis are essentially there. You have your boilers, storage water heaters that you can use as a heating plant. You can have indirectly heated storage tanks. There's actually a talk coming up right after this regarding stratified tank models in Energy Plus. The hydronic air coils, radiant emitters, water-to-water heat exchangers, and solar thermal integration if you want to get a little fancy with your combi systems as well. However, if you try and go and model a tankless combi right now, you'll kind of come up with against a limitation pretty quickly, and that's the fact that there is no module for tankless water heaters. And the way they're handled in Energy Plus is very simplistically. And so the current approach right now is essentially to model it as a storage water heater with a 1 gallon capacity and a constant combustion efficiency equivalent to the energy factor. And this is kind of the approach that I've seen used the most. And if this is not apparent right away, this is essentially assuming that regardless of your usage cases, regardless of the water heater, is that your water heater will be performing at the energy factor level, right? This is your efficiency. This is your annual efficiency. Now, there's been a number of studies in the last 15 years, basically laboratory and field demonstrations, basically showing that this is kind of the real world performance of water heaters, not just tankless, is a far cry from their energy factors, right? There was a notable study funded by PG&E, by the Ed Davis Energy Group, that compared tankless water heaters and storage water heaters monitoring in the field. They actually went as far as to recommend an 8% D rate for tankless water heaters if you want to get an estimate of annual efficiency. And this is actually the approach that's used with BEOP, at least the last time I checked. There was another study by Minnesota CEE that kind of did something similar, did a little bit more monitoring, a lot more data, but essentially similar conclusions in that, the actual real world performance, falls off quite a bit. And that's simply because there's a trend toward using less hot water. And on average, you have a lot of days where you don't use a lot of hot water. And so your part load losses for both tankless and storage water heaters are pretty significant. And they actually came up with some simple input-output correlations that you could use for predicting energy consumption that are actually pretty useful, and I just kind of want to make a plug for that as well. So again, the kind of the limitations of the current approach with Energy Plus, or if you were just to use an EF for predicting energy consumption, again, can't cover different usage cases. So can cover things like the variation with mains water temperature, which impacts your daily usage in different climates. And probably the limitation I want to talk about the most right now is kind of it's difficult to extend to combis. So last year, we had an opportunity as part of a NEA-funded project to get an updated look at tankless water heaters in the lab. There was an experimental component to the study, kind of looking at sort of what are the latest models, investigating some of these claims regarding half-inch gas line capability that you see in some product literature, in regards to what it means, as well as an energy and cost-saving analysis, which I'll talk about here. The experimental component and the results there, unfortunately, there's not enough time to talk about that, but the final report for that study has been published online by NEA. So if you're curious, you can follow this link here, and it'll take you to that. So in terms of modeling, right? So we know that, so I've already mentioned that we can't really use the energy factor to predict the energy consumption, and it's really difficult then to compare water heaters as well. So what we did was we applied something called the lumped heat capacity model that was originally proposed by Jay Birch from NREL. There was a report published in 2008 as a kind of a more accurate representation of a tankless water heater that's still relatively simple. That's characterized by kind of, three parameters. That's the thermal capacitance, C, that's the steady state efficiency, eta, and then the standby loss coefficient, UA. And this is relative to the heat exchanger and water relative to the environment. And I should clarify that the thermal capacitance refers to, this is the thermal mass of the heat exchanger and water of the tankless water heaters. The advantage of this method is that you can do some very simple tests to actually derive these parameters. For the testing that we did for that NEA project, you could do, we tried doing very similar a test profile where we do 4 draws, 2 different flow rates, and some maybe 2-3 hour standby periods. And from these draws, you can kind of infer what these parameters are. And I highlight at the bottom of the slide here, I kind of highlight what those parameters can look like for a non-condensing tankless water heater. Since it's been proposed by in 2008, it's been chewed on by in a couple of research studies, but it hasn't been widely used. So this was actually an opportunity to kind of apply it more broadly and see exactly what kind of capabilities there are. And again, we had an opportunity to look at multiple water heaters so we could see how their different parameters compared and sort of come up maybe with a generic characterization. So. Actually, let me go back. So I think one thing I do want to highlight here is that, once we fit the model to the data, is that we could usually predict gas consumption to within 3% or less, a lot of times less, depending on how reliable the controls of the water heater were. And what I mean by that is in regards to how reliably it could produce 125-degree Fahrenheit water in short subsequent draws. And so we compared it against our UAF measurements, which I just wanted to highlight really quickly here. And you can see in the temperature plots, which are the top left and the bottom two, are we can actually predict them relatively accurately. And again, as long as the water heater provides relatively stable water, then the model can reproduce its behavior pretty accurately. If you want to predict the energy consumption for draw profiles that are based on, let's say, gallons versus time steps, you will need an additional sort of parameter called we call it an overfire rate, but it's essentially just a temperature rise rate. Or there's the water heater will at the startup will fire at maybe 20-30% higher firing rate that it needs for steady state operation, just to bring up the temperature a little bit quickly. And so, with that model in hand, we can now couple it with, your hourly your hourly, not hourly, you can couple it with your annual domestic hot water loads. We did it using sort of loads generated by BOP, Energy Plus, 1 minute time steps, and, just to get those more realistic draw profiles, and then compare it to a number of different usage cases in a number of different locations where, again, Pacific Northwest, but also a number of locations around the United States where the mains water temperature varies, and as a result, your actual hot water usage varies as well. And we also looked at sort of, how does the usage pattern, how does the gas usage vary as a function of usage, is kind of highlighted in the plot on the right. And again, this model is robust enough that it can capture some of that behavior. We're able to show that, in sort of in terms of relative savings, that the tankless water heaters or will provide you the greatest savings in cases where you use the least water. And in terms of how it compares to the real-world performance, so I mentioned that study from Minnesota CEE when they came up with input-output correlations for their data, and this is what I wanted to compare on this plot here, which just plots the energy factor as a function of daily domestic hot water usage in terms of thousands of BTUs. So the red lines are actually those correlations from Minnesota CEE, and the yellow and blue circles are our simulation results for 2 locations. I think one is from Helena, and the other one is for Tampa. And then just to show that qualitatively that the model reproduces the results very accurately. The reason for deviations might be because the tankless water heater is a little bit different. Our characterization is based on laboratory evaluation, and again, the water heaters we've tested have had some combustion system improvements since then. And the Minnesota CE study didn't have as much data on sort of this on the far right region where on the high daily usage cases. You're also able to simulate the UEF test. So we were wondering whether you could sort of derive this input-output correlation, or sort of this, to kind of simplify the process just by running the water heaters through the 4 different UEF draw profiles. And we found that's probably not going to work, just because for the very low and low draw profiles that they're probably not as representative of real-world applications, and you end up with energy factors a little bit higher than what we saw in simulations and what's been observed in the field. But if you wanted to use, so the lump heat capacity model, it's simple for those already familiar with numerical integration and building energy modeling in general. If you want something even simpler, there's an inset plot here that gives you very simple correlations that you can, again, if you have your daily hot water usage in thousands of BTUs, you can predict your gas usage relatively accurately. Again, you won't have as much scatter, but you'll get the nice smooth curve through that region, and that should hopefully be useful for those interested in this. So that study is published. And then so the balance we've been working on the last year is on figuring out how to extend that model towards modeling tankless-based combis. And so the reason we want to do that is an ideal model for tankless-based combis is one that would reduce down to just the model for tankless water heater when there is no space heating calls. So we talked about this a little bit last year, but since then we've kind of tried to expand on it a little bit. And this slide just summarizes maybe the thought process behind it, where if we start off with the energy balance for the tankless water heater, and then we add an extra term for heat withdrawn by the air handler, we do the energy balance on the air handler, combine it together, and you end up with sort of this combined energy balance equation at the bottom, which now you have two extra parameters, which is the thermal capacitance of the air handler and the standby loss coefficient of the air handler relative to the environment. And it should intuitively make sense, simply because ultimately, if you think about what the air handler is and what the tankless water heater is, it's a heat exchanger with some water in it. And so it's, ultimately it's on the order of magnitude, the similar amount of metal and similar amount of heat loss coefficient and et cetera. So from intuitive perspective, it should work. So the advantage of this is you can, very similar to the tankless, you can potentially infer the parameters from limited testing. So in the last couple of years, we've been evaluating various combis, as well as something we'll refer to as advanced combis at GTI, where we do simulated use profiles, where we have coincident space heating and water heating loads. If you take that model and you kind of fit it to the data to infer those parameters, you can get reasonable agreement with predicted gas consumption on a daily basis. So the features are, nice advantages is you can capture part load operation of the tankless combis. It reduces down to the model of just the tankless water heaters with no space heating, and you can kind of start playing with controls a little bit as well, like simple things like outdoor air reset, and then strategies to remove the standby loss coefficients. There are limitations as well. The greatest ones is you're assuming constant steady state efficiencies for the combustion system. This in prior field trials has not always been the case, and then depending on the type of water heater you use and whether the system's optimized, your steady state efficiency can definitely drop off. So that may be something that needs to be improved within the model. One thing I do want to note is that the model parameters are really not physical or non-physical, and this is also true for tankless water heaters. And mainly is that there's not really a whole lot of benefit in comparing the thermal capacitance that was derived for one tankless water heater with another one, and it's more important to just look at their annual energy use as a comparison. And again, we've only had limited validation so far, but for the most part, it can capture the trends we've seen in the lab, but certainly more is needed, certainly with more like ad hoc combi systems as well. And just again, maybe I know I'm kind of running short here, so I'll just kind of highlight a few things. You can do things, play with control strategies. So we've looked at, what is the impact of off-cycle heating when you don't have space heating, in an open-loop system, and you need to kill Legionella if you cycle every 6 hours, which we had to do in one field trial. And it's a pretty significant energy penalty. If you can reduce it down to 24, if you can increase it up to 24 hours, then then a lot of the energy penalty goes away, but you're still sort of able to take care of that potentially. And again, broad, what are the broad features of this? Again, it has everything that desirable that you want. You can kind of consider it from space heating only, from domestic hot water, combi, and again, capture the nuances between all three approaches, where let's say the combi will give you the highest efficiency because it captures some of the interactive effects between the space heating and water heating loads, certainly for the colder climates. And then we also looked at, again, maybe control optimization, where you reduce some of the standby losses, and you can eke out a little bit of extra performance from your tankless water heaters. And again, with a model like this, you can capture sort of regional variation of the performance as well. And the other thing we've been using it for is comparison with alternative options, right? This is kind of what we were ultimately looking for. Not counting gas heat pumps, sort of the best, and combi, sort of the best gas heating options you have right now is a condensing furnace and a condensing tankless water heater. Well, with the modeling that we've done and testing we've done so far is that if a combi system is properly configured and optimized, you can actually get savings comparable or better than sort of this best gas options. And so again, very sort of useful with that regard. And so just to wrap up, again, so the combi work is still ongoing, so feedback is more than welcome, either right now or certainly as a follow-up. You can reach me directly at the email address there. Definitely further validation needed. We need to do a lot more uncertainty sensitivity analysis, certainly with respect to the combi work. And then there's still kind of a desire to develop some of those even simpler predictive correlations as well. And so just to wrap up, just to acknowledge the sponsors for this. Again, the tankless work was funded by Northwest Energy Efficiency Alliance, and the combi work is still supported by Utilization Technology Development. That's a consortium of natural gas utilities. So I guess I'll stop there and see, Kyle, if there's any questions that I can answer right now.
Great. Thank you very much, Alex. We had a couple questions come in. We have about 5 minutes for questions. So if there are additional questions out there, please send them. Please type them into the Q&A. You'll see the Q&A at the bottom of your screen. If you click there, you can type a question to me so I can ask it to Alex. So Alex, the first question is from Jim Lutz, and he's asking, what would it take to expand the draw patterns in the UEF to accurately characterize the tankless water heaters and combis?
This has to be explored a little bit, but I think what it's going to take is doing draws that are smaller than 1 gallon per minute and then shorter duration, because that's what those really are, is that you have random draws throughout the day that are very small. And maybe some of those are really not real hot water draws, and that's where, you don't even get the hot water to the faucet. But I mean, this is how people use hot water right now, and that's what it's going to take. I think the fact that, the smallest draw rate right now is 1 GPM, and I don't know if they go shorter than one gallon, I think might be the problem.
Good. We also have a question. Actually, we are a little short on time, so one more question. If there are additional questions, please join the chat room after this session. There should be a link to that. If you can't find the link, please let me know. The second question, if you could answer quickly, Alex, is from Jeff McGuire at NREL. He wants to know if there are any plans to incorporate this tankless model into Energy Plus.
Certainly open to it. We'll be looking at that in this coming year. I think we have a little bit of funding secured from the Natural Gas Consortium to do just that. So I will be looking into that, and maybe actually I'll be getting in touch with Jeff to talk about that.
Great. Mm-hmm. Okay, well, thank you very much, Alex. Our next speaker is Noel Merkit, who will look at improving performance of the stratified tank water heater model in Energy Plus. Noel is a senior research engineer in the residential buildings group of the Buildings and Thermal Systems Center at NREL. And his work there has focused on building energy modeling, including making contributions to DOE's Energy Plus software to make it suitable and performant for modeling residential buildings. He leads an industry working group to develop and maintain the Home Performance XML or HP XML data transfer standard and supports its adoption. He also leads the high-performance cloud computing and big data analysis capabilities for NREL's ResStock and CommStock building stock models. Noel is a registered professional engineer in the state of Colorado. He has a BS and MS in mechanical engineering from Utah State University. So please go ahead, Noel. Noel.
Thank you. You guys can hear me okay? Got everything on?
Yeah, I hear you fine.
Great. Wonderful. So yeah, I wanted to talk to you guys a bit today about some work we did to improve the stratified tank model in Energy Plus. And the first thing to talk about is there are several kinds of tank modeling, water heater modeling for storage tanks available, and several ways to do this. And there's kind of a complexity spectrum. There's everything from just, assuming it's all mixed and that we can do that. And that model is available in Energy Plus, all the way on the other end of the spectrum to CFD, which, if you want to understand very detailed dynamics of how different heat exchangers are working and everything, it's, that's the way to go. Kind of in the middle, or even more on the simple side, is the stratified tank model, which allows you to, use or to understand and work with the stratification of the temperatures in the tank. And especially important for certain kinds of modeling, and so the ones kind of on the simpler end of the spectrum tend to be the ones used in the like whole building energy model, where, the water heater is just one part of the building and we're trying to understand the energy use as a whole. So yeah, why would we choose the stratified tank? It's fast enough to be used in a whole building simulation. We have, it can handle that stratification, and it's kind of that just right balance of accuracy and speed. And specifically for us, one of the motivating factors was we wanted to model heat pump water heaters, and there are different, the coil is in one location in the tank, is adding heat lower, and there's heating elements at different elevations in the tank. And so it's necessary to accurately get the delivered hot water correct and the energy use correct for heat pump water heaters. So why does this matter? So we're doing this in the context of Energy Plus, which is DOE's kind of flagship building energy modeling software. It's being used in both residential and commercial buildings. It's more of a focus on commercial buildings initially, and we've been working to make it work better for residential buildings. For residential buildings, Energy Plus can sometimes take too long to run. In the cases of where you're at the kitchen table trying to talk to somebody and propose to them, some updates they can do to their home. We don't have 10 minutes, 20 minutes to wait for a simulation to run. And so the faster it can run, the better. So the slowness, in the case of Energy Plus and the stratified tank model, it was making it so that third parties weren't being willing to pick up using Energy Plus and to recommend and use heat pump water heaters. So we started looking into why, and we realized that for models with a stratified tank in it, over 90% of our runtime was just the water heater model, and the entire rest of the building was the other 10% of the time. So it seemed like the place to dig in. So the first thing is to understand, well, why is it being slow? So diving down into the math of it, we're calculating the temperature in the tank, means solving this differential equation. So it's, the mass of the water for that node in the tank, each of those slices, the specific heat, change in temperature over change in time, and the heat being added or removed from that node, whether through, flows in, flows out, standby losses, heat being added from the coil or the heating element or burner. So that's what all these, so it's kind of the net of all of the heat gains and losses on that node. So the way that the Energy Plus model used to work is, it's kind of like numerical methods 101. We're going to take the forward Euler method and just, march forward in time, change that differential equation into discretize it and just march forward in time. The problem is that to have it be accurate, we had to take like really small time steps of 1 second. And Energy Plus itself has a larger system time step of usually around an hour, from an hour to a minute. So within that system time step, we were having to take at least 60 steps and possibly many times more, depending on how long it was. And it was just taking a long time. We had to reevaluate all of the heat rates and everything in the tank that many, many times for each system time step in Energy Plus. So, we kind of went to the drawing board and were like, how can we make this work better? This is using pretty rudimentary numerical method. Are there other approaches that would work better? So we looked into a lot of different approaches for how to model tanks, and we're looking at specifically how to do better with the stratified tank, but, we're kind of open to a lot of things. Did some literature review, talked to a bunch of people. Eventually, we got in touch with the folks at TESS who have been, developing models for Transys, and we're really impressed with an approach that they took for their Type 1534 stratified tank model, kind of the numerical approach they used there. So we worked with Jeff Thornton there, subcontracted with him to get his knowledge and expertise on how to apply that within Energy Plus. So the new way of doing this, and the kind of secret sauce here, is that taking that previous differential equation, we could rearrange it such that it's in this form with these kind of generic coefficients. You could separate all of those terms that are in that heat rate, the Q net there, into parts that are multiplied by the current tank temperature, or the A term, or the current node temperature of that tank, and everything else, which is the B term. So that's anything in the adjacent node temperatures, which would use the previous time step, and ambient temperatures, anything like that would kind of fall into that B term. And by cleverly rearranging those parts of the equation, that, by rearranging into that form, that can be solved analytically. And there's an asterisk on that because, there's still parts of it, it's still an approximation. We're still assuming some things are constant that aren't actually constant, but that are changing slow enough that it's okay to take bigger steps in the numerical approximation. So rather than doing that forward Euler, we were able to take this pseudo-analytical solution or analytical solution of this approximation of the differential equation, and allows us to take much larger time steps. In our initial work, we went from internal time steps of 1 second to a full minute. So it's like 60 times fewer calculations of all of the heat rates and everything in the tank by switching to this method. And then the next thing that we did to help with that, on top of taking larger time steps, was we kept wondering, like, would it be possible to take even bigger time steps when interesting things aren't happening in the tank? It's just sitting there for several hours in the middle of the night. There's no hot water draws, just mostly standby losses. Or, to take smaller time steps to get better temporal resolution and more updates when things are happening, when there's large draws, when there's active heating going on. So, those, by doing that, we have to recalculate those A and B terms, which is sort of an expensive operation. And the way we did it was to, it's based on those current heat rates. It depends on all the things happening, but a lot of them are changing slow enough that we can take a bigger time step. So what we did is determined calculated how much could the temperature of each node change before something interesting happens, like we hit a set point and the heater kicks on. And then we're able to make a kind of rough linear approximation, going back to that previous differential equation, kind of rearranging it to say, well, then how big of a time step can we take until we get to that point of something interesting happening? And then, in reality, in the code, we actually back it off a little bit. We don't go all the way to that point. We go, 9/10 of the way or 95%. So that, we kind of work up to it. And what that allowed us to do is make it so that the time step within the tank could be adaptive. And as a result, we were able to switch it to where we can have a time step of 10 seconds if things are happening quickly, there's draws, there's heating happening, or both at the same time, or 30 minutes if the tank is just sitting there. And that allowed us to gain even more speed improvements, because for most of the time in an annual simulation, there's not a lot happening with the tank. And it's just kind of sitting there losing heat slowly through the walls, which doesn't take a whole lot of computation to get right. So at the end of the day, the question is, how much faster is it? Originally our models were running on the order of 2 minutes, which was a little too slow for some of the residential buildings that we were working with. We wanted them to get answers much quicker. By reformulating, we got that down to about 30 seconds, and then stepping it back, we got it around with the adaptive step size. That cut it in half again to about 15 seconds. So this is for a whole building simulation, 10-minute time steps, for a single-family detached residential building with a heat pump water heater, which kind of seemed to exercise this the most. So that was a really good outcome for us, because that meant that heat pump water heaters could be used in some of these models, and it would be that we could recommend them, we could understand their energy use while not being held back by waiting for the simulation to run. So the other question is does it come up with the same answer? Is the answer right? This plot is very uninteresting. These are a couple of different heat rates and temperatures in the tank for a heat pump water heater. And there are 3 lines on each of these. And for the old model, the reformulated model, and then the reformulated with the adaptive step. And you'll see that they're all pretty much just right on top of each other. There's a few places where it varies just a tiny bit, and there's large, fast draws, but for the most part, the answers come out almost exactly the same within a fraction of a percentage point, which was a really good outcome of this. So that is the end of my presentation, and happy to take questions.
Hey, thank you very much, Noel. We've got one question in from Gary Klein, and I'll read it to you in just a moment. Just a reminder to the audience: if you have questions, please submit them using the Q&A tool at the bottom of your screen. Gary asks, he wants to know, what does the model predict for the temperatures below the lower element in an electric storage water heater? Mm-hmm. And the same question for condensing gas storage below the internal flue pipe.
Yeah, it's a good question. I can't give you an exact number right now because it depends on of course, on the tank being modeled and all the inputs to it. But if the element is, it depends on how you discretize and how many nodes you break the tank into. If the lower element is in a node above the lowest node, then you will see those temperatures. The temperature will be lower below that element, and it will, be closer to the inlet water temperature, the mains water temperature. But there are, of course, some conduction that happens there. So, and that's modeled so that it's not quite the main temperature. But yeah, it does account for that as long as you have enough nodes in your tank to have the lower element in a node above the lowest node.
Okay. Jim Lutz also asks a question. What about changing to 2 nodes, a cold and hot node that vary in volume? Yeah,
that is one of the, and I probably should have mentioned that earlier in the slide, that is one of the models that we evaluated in the process of doing this work. The reason why we chose stratified tank was because there are many other models there are many cases where the stratified tank is used in Energy Plus already. A lot of that code already existed, and we chose to make the investment to make that model better rather than implement another model that wasn't already in the software to meet the same need. But I've heard really good things about the 2-node cold and hot water with the variable volumes. That was one that we did talk about considerably when we were looking at this. In the end, it ended up being a decision about the software and what would be best to kind of contribute back to Energy Plus to improve what was already there.
Great. Thank you, Noel.
Sure.
Yeah, thanks very much, Noel. Our next speaker is going to be Kashif Nawaz. Kashif will be talking about something that's really important for modeling, which is having experimental uniform energy factor data at various ambient conditions. And Dr. Nawaz is a senior research staff at the Energy and Transportation Science Division of Oak Ridge National Laboratory. He received an MS and PhD in mechanical engineering from University of Illinois at Urbana-Champaign during 2010 and 2013, respectively. His research interests include heat and mass transfer through porous media, two-phase flow, transport phenomena, and alternative refrigerants. He is a member of ASHRAE and ASME. Before joining ORNL, Dr. Nawaz has worked as a senior heat transfer engineer at the Heat Transfer Center of Excellence at Johnson Controls, Inc. In his present role at ORNL, he's actively engaged in the research related to heat exchanger design, separate sensible latent cooling systems, dehumidification, enhanced phase change processes, low GWP refrigerants, and water heating. He has more than 30 publications in fundamental and applied thermal fluid sciences. So Kashif, the floor is yours.
Yeah, well, thanks, Kyle. Thanks for the introduction. So as Kyle mentioned, that I'll be talking about the performance evaluation of the heat pump water heaters under non-standard operating conditions. So there's a lot of information available. For example, when the heat pump water heater is operated, let's say on the in a standard 67 degrees, about 60% relative humidity. But when we talk about the performance under non-standard operating conditions, there can be some degradation, and that's really the main focus of this discussion. This is a quick overview of the content. I will start with the motivation and the background, why we are working on this problem. Briefly discuss about the experimental setup, the experimental procedures, and then I'll jump into the results, discuss the uniform energy factor, compressor runtime, the potential thermal stratification behavior you can see, and then in the end there will be conclusions. So by far, heat pump water heaters have been found to be one of the most efficient technologies. Water heating itself is important business because obviously there is about 10% energy is being used right now. All the energy which is used by the building, water heating is at least 10% of that energy usage. And when we look at different water heating technologies, of course, the heat pumps, water heaters, they might have a higher upfront cost, but when you look at the payback period, that's much lower compared to some of the other competitive technologies. So the heat pump water heater itself, well, essentially it's a heat pump used to heat up the water. But when you look at the different components, it's a more involved and highly complex system because unlike the conventional air source heat pump, you also have to deal with the storage tank, appropriate control system. And then oftentimes the heat pump system is backed up by electric resistor heaters, which are there as a to complement whenever there's a sudden increase in the demand. So all in all, it obviously becomes a very complicated system. And on top of that, obviously, when you are operating it under extremely low ambient temperatures, there is a probability of a lot of things happening on the operator coil, which means that you can have a lot of condensation and frost formation, which can obviously lead to the degradation of the performance of a standard unit. So if we look at the what happens when you operate at the low temperatures for the conventional air source heat pump, it has been established that you will see some major degradation in the performance. So on this figure over here, you can see how the COP is decreasing as you decrease the outdoor air temperature, essentially the dry bulb temperature. And this figure over here presents the results for 3 different locations. The reference is listed over here. One thing I want to point out that when we are operating at the lower end, when obviously the dry bulb temperature is low, the role of relative humidity becomes important. And one of the reasons for which for the 3 units we see different performance at lower end is essentially because of the different relative humidity specific to that region. What happened essentially at the lower end, of course, like if you're talking about the cold climates, there is a higher probability of frost growth on the condenser, on the outdoor coil, and that can obviously lead to the reduction of the capacity as well as increased fan power, which can lead to a lower performance. So when we talk about the heat pump water heaters, now they are normally placed in the areas where the temperature stays higher, but there can be situations where obviously you can have like one in a time situation where the temperature can go low, and it can go low to a point where obviously we can start seeing phenomena such as condensation on the evaporator coil, which is essentially going to degrade the performance. And worst case scenario, if the temperature is really very low, then we can see there can be frost formation, and which can obviously decrease the performance even further. Along with these 2 aspects, there is also going to be a substantial heat loss. The existing systems, they obviously come with very good thermal insulation, but obviously when you decrease the ambient temperature, there can be some implications. Now, beyond these conventional aspects, I also want to highlight, because of the emerging interest in some of the refrigerants which are flammable, there is a possibility to put these units outside of the homes where obviously they will have to go through the same issues which are seen by the air source heat pumps. And also want to highlight that the UEF and the COP, Uniform Energy Factor and COP, are two different parameters because if you just look at the COP, that will be a good measure of the steady state performance, but UEF also gives you an idea like how much is the heat loss from the tank. So effectively, UEF is a better parameter to quantify the performance. And another thing, most of the OEMs, they always provide a cutoff limit. The control system is set that if the temperature goes beyond a certain limit, the heat pump turns off completely, and then all the heat is provided by the electric heat. So for this study, we specifically requested a special control system which can obviously assist us to operate the heat pump system even the temperatures which are extremely low compared to the conventionally available control systems. So that being said, I want to highlight that most of the results we are presenting, or all of the results we are presenting in the following slides, they are essentially based on the performance of the heat pump. And we obviously made sure that the electric heater does not participate. The experimental setup of the procedure, if you look at this figure over here, we had a setup which was quite highly instrumented, both on the refrigerant side as well as on the water side. The setup was placed in an appliance chamber where we had a very good control over the relative humidity as well as of the temperature, dry bulb temperature. On the refrigerant side, we were monitoring the suction and discharge temperatures, the flow rates of the refrigerant. On the water side, we were able to control measure the inlet-outlet temperature of the water flow rate. And also, we had a thermocouple grid inside the tank to monitor the temperature or thermal stratification at different conditions. Then, of course, as I mentioned earlier, we had a control of the ambient conditions by controlling the dry bulb and the wet bulb temperature. For the performance evaluation, we used the DOE standard criteria to establish the uniform energy factor. Well, first we established the first hour rating, and based on the results, we used the median usage pattern prescribed by DOE. And this table over here shows you the drop pattern used in this study. Okay, so this is the first result I'm showing over here. The uniform energy factor for the heat pump water heater at different temperatures. You can see that when we go away from about 67 degrees temperature, which is really the standard procedure, and go to the higher range, on the other end of the higher temperature, there's a big change in the UEF. It becomes better, which is expected. However, when we go towards the lower range, there's a very specific pattern, as you can see, that the UEF decreases. We went up to about 40 degrees F, and we are still running some tests even at lower temperature. But there was a major decrease in the UEF, as can be seen over here. And I'm not showing any images, but we obviously start observing some clear indication of condensation when we were close to about 45 degrees C, and at this 40 degree F temperature, we essentially saw a lot of frost on the evaporator coil. Now, I want to mention that this is really a study where we were mainly focused on the ambient dry bulb temperatures. We were obviously monitoring the relative humidity, but that was not the main focus. And we are actually conducting another set of experiments really to see what happens at with respect to the relative humidity when we are operating at the lower ambient temperature. And in that case, obviously, we are mainly focusing at temperatures below 45 degree F, because beyond higher than that, the relative humidity is not that critical. We might see a little bit condensation, but the problem will be much more interesting if we are operating at the lower side. So the UEF obviously is established based on the total energy input. 24 hours test accounts for the total energy input into the system. And one of the important parameters is really the compressor runtime, because that directly relates to the amount of energy which has gone to the system. So from these experimental results over here, you can see that this was essentially the start of the test, and we can clearly see over here that when the ambient temperature is low, the compressor runtime was higher in the case of 40 degree F experiment. While when you compare it with something like 78 degrees, the runtime was much smaller. So we have run a series of experiments. There's actually a similar pattern. There are some outliers, and we are essentially in the process of confirming that data. And this is another important aspect I want to indicate over here. This is really the thermal stratification after about 30 minutes to 1 hour standby period. And in this case over here, again, there are some there's some distribution over here, but one thing we can conclude over here that obviously the thermal stratification is significant, or is much higher when the outside temperature is higher, in the case of 78 degrees. And when we go towards the lower temperatures, not only the compressor runtime is higher, but also the thermal stratification is not significant. In our previous studies, we have established that having a higher thermal stratification is important because that can lead to a higher UEF. And that is essentially also confirmed by some of the results over here. This is just obviously one set of experimental data which I'm showing over here, but we have essentially analyzed the thermal stratification at different situations, such as during the draw time, right after the draw time drop pattern, and obviously when the system has been on a standby mode for a couple of hours. Okay, so moving on towards the conclusions, essentially we have established that the ambient conditions, they are important. They can impact the performance of the heat pump water heater. Unified energy factor and COP, both of them, they degrade because of the ambient temperature as we go towards the lower end. The compressor runtime is an important parameter which must be accounted for when we are looking at the overall performance. And most importantly, the thermal stratification behavior is significantly different when we look at the different ambient scenarios, and that obviously can lead to change in the performance. With that, I would like to acknowledge our sponsor. This is a CRADA partnership with A.O. Smith and U.S. Department of Energy. Our program manager, Tony Buza, has been supporting us for this activity. And with that note, I'd like to conclude, and I'm willing to answer any questions. Thank you.
Great. Thank you very much, Kashif. I haven't had any questions come in from the audience on the Q&A. So if you have something, please submit it. I'll give people a minute to while I mention that apparently the link to the chat room is not visible to the audience, and so I'm going to try to send you a link to it. You can also reach the link to the chat room that will start in just a few minutes by going to the engagement hub, which is you go to your browser, and that's how you got to this. If you go to that engagement hub, there should be a link. I will also try to post a link to the audience in just a minute. Actually, I hear that Kate just sent the link to everyone. So if you don't see it, please just submit a question and I'll point you to it. So great, Kashif, we have a question from Abigail Decken at the EPA. She asks, have you checked to see how these results compare to those derived with NEA's colder climate measurement?
Yeah, well, we have not made any comparison yet, but we are in the process of looking at some of the other studies which have been conducted in this area. All I know that when we were having a discussion in our last hot water forum last year, there was actually a session focused on these testing procedures, and one of the things was brought up that was the UEF essentially decreases in more like a linear fashion, when we go towards the lower temperatures. In our case, at least up till now, we have seen more like polynomial behavior, if you will. It's not a linear line, but essentially we need some more data points to do a better conclusion, to get a better conclusion. And another thing I want to highlight that it's very important, especially when we are talking about the lower temperatures, to have the same obviously relative humidity if you want to make a comparison, because let's say if I'm operating at 40 degree F, I am having 60% relative humidity versus, let's say, 80% relative humidity can make a big difference. So the conditions, they have to be more or less the same in order to make a fair comparison.
Okay, thanks, Kashi. Ivan Calder from the Atmospheric Fund asks for a quick clarification. He's wondering, can you repeat when relative humidity is not a significant factor?
Yeah, so in this case, obviously we were trying to maintain the same relative humidity. In some cases, we were able to do that, but you obviously need a very good environmental chamber in order to have fairly good control, on the conditions. And then it's also important that those conditions, they stay uniform for the whole test, which is 24 hours. So it's a little, I would say, tough job when it comes to making sure that we have a very precise control on both dry bulb as well as the wet bulb condition. But yeah, we actually we can certainly repeat these experiments with the same relative humidity values.
I mean, I would expect that when the humidity is low enough that you do not have any condensation on the coil, then it's pretty independent of relative humidity.
Right, and at that point, I would say the most significant factor will be the heat loss from the tank, and that's another thing. If we want to look at the contribution of the performance of the evaporator degradation versus the heat loss from the tank, those two parameters are also a little bit tough to see their impact separately. But yeah, to your point, Kyle, obviously when we don't have a lot of moisture in the air, then the only factor which can potentially degrade the performance is essentially the heat loss. And then, of course, as in general, for all the heat pump operation, when you go to a lower end temperature, even in the case of air source heat pump, the performance will degrade.
I think we have time for one more question. Jim Lutz is asking, what sort of parameters would be necessary for modeling, like the previous speakers talked about?
Yeah, so in this case, a very important parameter which has to be established accurately is the evaporator performance. Because we are essentially talking about the more like a transient phenomena, where obviously when the heat pump is running, you can anticipate that the frost will be growing, and over the period of time, the capacity will be reduced. So I would say that this is essentially an important problem when it comes to the modeling, but at the same time, it requires a little bit more in-depth understanding, what happens to the evaporator coil parameters, like the previous presenters, they talked about. There has been some modeling effort. We have done to some extent at Oak Ridge as well, where we can establish the performance under standard operating condition, where obviously we don't have to deal with the extreme humidity issues. But when you essentially talk about this scenario where you have a lot of phase change happening on the fin surfaces, then it becomes a little bit more involved. And in any case, any model we talked about, that has to be validated based on the experimental data. And so it's essentially an interesting problem, and I think there are some efforts ongoing in this area.
Good. Well, thank you very much, Kashif.
Thank you.
Thank you. And that concludes our seminar today. I want to thank our speakers for the presentations and the attendees for participating. Reminder, we will be reconvening in the Zoom chat. Check your Q&A at the tab for the link to that Zoom chat. And I want to remind everyone also that today at 3:30 Eastern, 12:30 Pacific, we'll be having the Shameless Commerce Happy Hour, and participants can register through the Engagement Hub platform. The Shameless Commerce is returning again this year. It'll be packed with rapid-fire presentations on new products and services Shameless Commerce is an opportunity for companies to present a short 2-minute infomercial on their latest and greatest, and audience participation will judge the best pitch. There's actually a couple slots still open, and if you're interested in those slots, you can contact Hannah Bastian at ACEEE. If you need that link, please send me a message or and yeah, we'll conclude there. So I hope to see people in the chat and at the Shameless Commerce session this afternoon. Thanks everyone for joining today.
Thanks.